language. You know, there's one word that means 8 different things, yet we have 100,000 commonly used words. Okay, so on 204, that's a plane mirror. In other words, the one you see at home. Unless you're Sarah and you have like one that blows up your face to 12 times the size so you can put your makeup on. Okay? Which a lot of women do. I'm just making fun of you. I know you don't. No. Anyway, that's a plane mirror, a flat mirror, a straight mirror. Okay? It's not in a fun house. It's not all curved, so you see distortions and things like that. And you might think, well, this is kind of silly, but there's a lot going on here. You've got choices. Is this upright? Or is it an inverted image? Like that light bulb I showed you yesterday that Alicia loves so much. Okay, it actually inverted that light bulb and made it show where it actually wasn't. That was an image of the light bulb produced by the mirror. In this case, you know when you look in a mirror, your image is upright. Did you know your brain actually sees things upside down? Do you know things get inverted in your eyeball and your brain processes them the other way around so things look upright? Did you know that? It's kind of weird. No. Your eyeball sees it upside down in the back of your retina, then it goes to your brain and makes it right side up again. Exactly. Here's the question. What if someone was born and they took their eyes out and turned them 180 degrees and then fastened them back in? Would they see everything upside down? Or does their brain reprocess it and now they just see it just like we do? I think the brain would self-correct too.
How would they know that?
It's kind of cruel to try.
How would they know that everything?
Because there's smart people like physicists who look it up and figure it out.
They look it up on Google?
No. Okay. Is this a real or a virtual image when you look in a plane mirror?
Virtual.
Yeah, and it tells you here, because it's actually behind the mirror surface, it's virtual. Okay? The definition is an image that can be projected onto a screen is a real image. As you know, this isn't projected in the wall behind you. It looks like if you stand 3 feet from the mirror, then as far as you're concerned, you see yourself 3 feet inside the wall, right? Okay? But it's a virtual image. It isn't actually, the light rays aren't actually focusing back there, because I mean, that's actually, you know, some other room probably, right? Your wall is only, you know, 8 inches thick or so. And size. We're going to look at curved mirrors. That's all your notes are going to do. Is this smaller? The same? Or is it a larger image? It's the same. Okay? These are called, as you know, we looked at some straight lines and I showed you lasers, and this is just one photon. And as far as you're concerned, there's your eye. You see the top of your head here, but it's actually bounced, right? So when it's virtual, we draw it with dashed lines. The actual light ray goes like that. Same thing, what if you want to look at your feet? You actually look at this light coming from your foot. Let's start there. That photon bounces off this mirror and right into your eye. So if you were, say, 180 centimeters tall, how big of a mirror would you need in order to see your whole self? It's exactly half of that. Yeah, that's all you need. You just need a mirror half the size of you, and you can see your whole self. So, not something practical in life you're ever going to need, but you know. No. Just, it's always the little things that just, you know, they're unimportant, that won't be on the test. Everyone's like, oh, well, let's do this for like 3 hours. Okay. Well, that's about that. Graph paper. If you got it, great. And if you got lined paper, that's fine too. But yes, you need this. Absolutely. That's why I'm saying, you know, these are notes. So we got, first we'll start with a concave mirror. Now, just looking at that, you don't really know if that's concave, i.e. makes a cave, or is it convex, until I tell you what side we're looking at. This is concave because we're going to be focusing on the left side of it. So this forms like a cave over what's going on, so we call that concave. If I was working on the right-hand side of it, it would be convex. That's just something you got to remember. Okay, some definition, terminology type stuff. That's what we call the vertex. And if you've done parabolas, which you all have, then you know that's the point. If this thing was flipped 90 degrees and went up or down, that's the point where the line stops going down and starts going up, or vice versa, if it's upside down. That's just a vertex. It's not really something critically important, but you will get a question in the book that says, what is the name of the line that joins the vertex to the C, the center of curvature of this thing? And you're going to go, where's the vertex? Well, now you know. This is the principal axis. Okay, an imaginary line like halfway down through this mirror. And we're going to assume this thing is like an arc, like a slice of a circle. But actually, the best mirrors are actually parabolas. Okay, but you don't need to know in either case. It doesn't really matter. Here is C, and that is the center of curvature. Come on, pen. In other words, the center of the mirror. If this thing was a whole circle, okay? Just the center. Well, we don't. And I guarantee it's not. But again, I didn't use any tools to draw my section of circle either, did I? Okay? And believe me, when I see some of the way you guys are going to write some of them, it's going to be a lot messier than this. And then it's my job to try to mark it, right? Okay? What else do we have? We have another dot here that's actually called F, which is the focal point. You're not writing this down, Dan? Okay, that's an important point. This is what we're going to use to draw stuff. Parallel. My pen is still on holidays. Parallel rays. Now, incident is a word hopefully we're kind of familiar with now, right? Incident on or upon, but let's say on, mirror will always reflect through F, the focal point. And this is how you guys are going to draw these things, these images, and where they're going to occur. So I'll use a different color. Graph paper is nice because now I know I can draw a nice parallel line that's a ray coming into that mirror. And what does this say? That's a parallel ray. It'll reflect off this mirror and go through the focal point. That's just what always happens. Okay? So a piece of light comes in, bounces off this mirror, and goes right through F. Any parallel ray. So let's say there's a ray down here. Same thing. Hits the mirror and bounces right through F. Now, when you guys do this, I'll tell you again, but I'll tell you now, do it. I'm not using a ruler, but they look pretty straight, like straight enough, okay? Accuracy is key. You don't need a ruler because you don't need to measure anything, but you should be using a straight edge. There's a nice straight edge. Edge of your book. You know the cheap man's ruler? Take a piece of paper, fold it twice, now you got a straight edge, okay? There's no excuse to have like sloppy lines because your image is not going to be in the right spot and you're going to get the wrong answer, which is more important. Okay, last little thing in this picture is little f, which is the distance from the mirror, i.e. the vertex, to f, the focal point, okay? And that's what's called the focal length. And it has applications in things with cameras, lenses, okay? Little f is the distance from the focal point to the vertex. Okay, so this, by the way, now we're going to call this a concave mirror. And to denote a mirror, sometimes they'll do this with lines on the back showing you which side is reflective. Okay, but going forward, we'll just do a line. So I don't want to get too much on the same picture. So I'm going to do this again. Here is the focal point. This is one ray you're going to draw to help produce this image. The other one you're going to draw says this. Conversely, all rays going through F, the focal point, guess what will happen with those? They will reflect parallel, right? So this is the other ray. You basically need two to draw these images, and this is the other one. So I don't care where it goes, but if it goes through F, it bounces off the mirror and becomes parallel. I can do a little better. Hang on. Okay, as neatly as possible. This guy comes through F, hits the mirror, and goes parallel. Okay? These two pieces of knowledge, which is essentially the same thing just in reverse, that's how you're going to draw some images. So, drawing an image outside F. This is one. Well, this is what happens when the image is past F. So maybe a little bigger. Okay, somewhere down here we're going to have F, which is on our principal axis, but we're just not going to label it. And we're going to have an image. And for simplicity's sake, let's say it's a pencil, a person, I don't know. An arrow is as good as anything, and in a lot of the books that's what they use. Where's this image going to be if I put that arrow there outside the focal point in a concave mirror? Well, what do we know? Nothing. You know this ray comes in parallel and bounces through the focal point. So the top of this arrow goes parallel and bounces through F. Okay? And also a light ray that goes through F bounces and goes parallel. Now I didn't draw the first one long enough because wherever these two meet, that's where the arrowhead image will appear. So one ray will go parallel, bounce off the mirror, and go through F. The other one will go through F, bounce off the mirror, and go parallel. Now, of course, we're not measuring this, so everyone's going to have their arrow a different distance from this mirror and a different distance from F. But wherever these two rays join, that's where the image will appear. So some of you guys might have this before the arrow. Some of you guys might have this on left of the arrow, let's say. Okay, it doesn't matter, because everybody's picture is going to be a little bit different. But wherever these two rays, as straight as possible, you want to draw these, that's why you want a nice straight edge, that's where this thing is going to reappear. Okay, that's where the arrowhead's going to be. Now, you don't really know this yet, but it will actually invert it. Okay? So this thing will look like that. That's where the image will appear. And like I said, if yours is before the arrow, that's fine too. It's just that's how the picture goes. Okay? So those two rays should be sufficient to draw an image. So this image, which I did in a different color, is it real or virtual? If it's on the same side as the object, we can project that on a screen. It's not on the opposite side like our plane mirror. That's going to be a real image. Is it inverted? Well, I drew it for you, so yes it is. And I'll show you in a sec. And is it smaller or larger? And this is where you want to be careful drawing your rays. Okay? Here, I don't really know, okay? But let me just, looking at the bottom one, if I go parallel with that and draw that here, it looks like it's going to be up there, okay? For the bottom ray going through there, it looks like it's going to be there. It looks like it's a little bit larger in this case. But if yours looks smaller, like I said, that might be okay. Because different things happen depending on how far that arrow is from F. Okay? So I'll just put a question mark there. It just depends. So that's one example of what can happen. We got a couple more to do. But let me grab my mirror for a sec and just maybe have somebody confirm what's going on. Let me just pause this. So she's well beyond F, because I know F for that mirror is only about 2 feet away. She was inverted and she happened to be smaller. So maybe her arrow was a little bit closer here and her arrow came in like that. That's okay. All right? So outside F, that's one thing that happens. Now guess what we're going to do next? Yeah. Because something's different happens. And you guys, you might have witnessed this as a kid, because I think most kids do it, but you don't know what I'm thinking about till I say it. But I'll hold that thought. Image inside F. So here's F. Draw another mirror. There's our principal axis. Now we're going to put our image here. And how do we draw our image? Just two rays. First one goes, bounces off the mirror, and goes through F. Okay? And the second one goes through F and bounces parallel. This one that's parallel bounces off and goes through F. Yes? Well, the light from this tip of this object hits the mirror and will bounce through the focal point. So what light is going through the object? Yeah, I know. So I'm not going to draw the ray from the bottom part because it gets a little confusing, but do we see where this image is going to occur? Sorry? Well, we're going to take one here that's parallel up here. It's going to go right through the tip of this object, and that's also going to go through F, isn't it? Yeah. So I just got two of the kind of going parallel through F. But you can also say that this one goes through F this way and then will go parallel. But that happens to be one that's right at the tip of this object. Do we see where these rays converge here? Okay, we need another volunteer. So don't all stand up at once. Let's go have a look and see what happens with this image when someone's inside F. Dan, thanks. Go on. Well,
why don't you set it up so that
turn around. Can you stand over there and see yourself? You're up inverted. Now put your head so it's in the center of the mirror. Like, put your head centered, and then walk towards it until what happens? Keep going. Yeah, and don't get too close because you'll see in high definition every little blemish on your face. Okay, so you start back there again. Does anyone else see this? You have to be exactly where this mirror is sitting. So right now we know he's past F, he's inverted. It might be larger, might be smaller, probably smaller. And as you come towards it, explain again what happens. Well, now he's right side up and he's a lot bigger. Okay, so where is that image? Well, where this line lines up with this line, that's where they meet. And as Danon said, he was right side up and enlarged or magnified, so that's where the image actually occurs. So this is behind the mirror, so it's what we call virtual. And larger, and now there was one point right there, it was probably right at F, where that image flipped. It was inverted, and now it's magnified. So that's what, like I said, people have these at home for makeup mirrors because you want to see, yourself magnified. Concave mirrors is what they use. Not that big, of course, but... All right, so this one, a little bit tricky, huh? Well, got to know how to do that. Just 2 rays, that's what happens. Okay, if your notes are really, really terrible, there is a picture in the book. Okay? Can I make this bigger? No, okay, I gotta make a new one. Okay. Let's do some real physics, even though that is physics, but this is an equation. Everyone see that on the back of their book, on their formula page?
No.
That's the first formula in your book. That's the mirror equation. It also works for lenses. So what this tells you is the relationship between the lengths of the object, the length of the image, and the focal length of this mirror in question. Because every curvature of a mirror will have a different focal length, of course, right? Okay, so DO, distance of, what do you think O stands for? Yeah. Or let's go object distance. I, that is the image distance. And this isn't named after anybody. It's not, I don't know if there was a person that first discovered it or he chose not to have his name, or I should maybe say, maybe her. I don't know, but it's just a mirror equation. There's no name. And F is the focal length or the distance of F, right? But we usually say focal length, not focal distance. Don't ask me why. So, example. I just got one. If you need another one, there's a different one in the book. An object is 75 centimeters from a concave mirror. That's the ones we've been doing. With a focal length of 25 centimeters. Where does the image form? How many variables in this formula? 3. DO, DI, and F. You got to know 2 of them. Do we have 2 numbers in there? You bet. You just got to know which one's which. I'm trying to solve for what? Where does the image form? In other words, what distance from the mirror is the image? What's DI? An object is 75 centimeters from the mirror. That's DO, right? That's the object distance. And a focal length, well, obviously that's F. The only nasty part about this formula is it's all reciprocal stuff, right? It's 1 over. So we got to solve this thing for DI. So you could try to get DI by itself, and we probably want to. How do I get rid of 1 over DO? Just to subtract it, right? It's the easiest way. And then 1 over DI is 1 over F minus 1 over DO. Okay? Then I'll throw my 2 numbers in there. 1 over DI is, F is 25, DO is 75, Then what? Can I make this a number in my calculator? Sure. Should be one operation. Because this thing does dead mass, I can just do that. And it'll do the dividing before the subtracting. 0.0266666666 is, what was that? 0.0, looks like 6 repeat, right? So you can cross multiply that. So that's 1 over, but do you guys, are you familiar with this button over here? 1 over? Yeah, feel free to use it. Okay? There's a 1 over button on this calculator. You might have it on yours too if you got a different one, but 1 over, that. Okay, so well, let's do it the long way. 0.026 di is 1 times 1, right? Cross multiply, and then divide both sides by 0.026. So di is 1 divided by, but make sure you put in lots and lots of 6's. Don't just put in 1 or 2, otherwise you get the wrong answer. Okay? The 1 over button? Need to know basis? Okay, do the 1 over button. Even that, look at that. It's still off a bit because I didn't put enough 6's, right? So even that is, I mean, you're going to round it, of course, to 37.5 either way, but it's a nice button to be familiar with. Okay, what's going on here? Here we go. Anyway, it's 37.5. What units? Centimeters. That's where the image will form. If the focal length was 25, okay, the image was 75 away, whatever image that was, then this will be, it's probably going to be inverted, and it'll be 37.5. Now, what happens if you get a negative number, do you think? Good guess, yeah, because one of those in the questions in the book will be like that. Okay? That's enough for today. Let me just write this down and then I'll answer your question. Okay, when you're drawing these diagrams, guys, neatly, use a straight edge. And I haven't talked about a convex mirror. I'll touch on that tomorrow, okay? I'll just write those questions down. If there's one on a convex, just hold it off till tomorrow. Hmm?